I'm Jeremy Wyatt and I'm Professor of Robotics and Artificial Intelligence. Very simply, people know about robots. You know about robots in car factories, for example. And a lot of people by now will have heard a lot about AI, the business of making machines that are intelligent. And in a nutshell, what we do in this lab is we put the two together. So we put the smarts in robots. We trained it using what we call data-efficient machine learning algorithms to grasp objects that it has never seen before and to do it dexterously. So this might be, for example, a teacup, and you've shown it how to pick up a cup before or to pick up something with a handle, and it looks at that cup with a depth sensor. It only sees maybe a very small proportion of the cup, so maybe 20% of the surface, and it comes down and it can pick it up by the handle, brace it with its finger, but it'd be nice and polite with its pinky out here and pick it up so that you can have your teacup. Every time you put a little bit of intelligence into the robot, you open up a new world of possibilities for it in terms of the tasks that you can perform.
My name is Luke Carter. I'm a research scientist in the Advanced Materials Processing Research Laboratory here at the University of Birmingham. So we focus on two key technologies, the laser powder bed method and the laser blown powder method. And in very general terms, this is 3D printing with metals, basically. The idea is very simple. You start with a CAD file, a 3D computer file of your shape that you want to make at the end of the day, and you virtually slice that into a whole sequence of two-dimensional slices of a thickness. You do that, you generate your laser path for each one of those slices, so the laser sort of colours in, if you like, each one of those slices. Then we feed that information into the machine. And what the machine does, it spreads down a very thin layer of powder, and a computer-controlled laser melts that first slice. Then it lays down another layer of powder, and it will melt the second slice of material, and it basically forms each layer, so it's doing that process over and over and over again, so maybe a few thousand slices in a typical CAD file that we put through to build up a final shape and net shape product. It's just another way of metal forming. I don't think anyone at the moment is saying this is going to replace every single method of metal forming. Every way of manufacturing has its own advantages and disadvantages. This is just a different set of rules, and it can do some cool things that we can't do any other way at the moment.
My name is Bob Stone, Professor of Interactive Multimedia at the University of Birmingham. This particular facility is designed to train future defence medics to help with casualty evacuation. And what we're trying to do is we're trying to blend the best of the real with the best of the virtual, using common off-the-shelf components in virtual reality, such as, for example, the HTC Vive. You can see now that I'm actually inside a virtual Chinook helicopter that's in flight, and here we have our casualty. I'm seeing the casualty as a virtual model, but as I press on the casualty, I can actually feel the rather clammy skin of this mannequin. We're working with the Royal Air Force, Tactical Medical Wing, Bryce Norton. We're working with the Royal Marines down in Devonport and the British Army. And the plan is, over the next few months, is to actually roll this out for beta testing trials with actual trained defence medics. So the idea is that we want to be able to measure what they learn in the virtual world and how well they transfer those skills and their knowledge to the real world. So it's, again, blending the best of the real with the best of the virtual.
My name's Carl Dern. I'm a reader in mechanical engineering, and I lead the Mason Institute of Tribology, where we're looking at making mechanical systems more efficient by improving the frictional properties between surfaces. So the really exciting thing I think about working in tribology is that, as I said earlier, it affects all aspects of life. So we're looking at how we can perhaps develop therapeutic treatments for infertility by understanding fundamentally the tribological interactions within that system. So a lot of our work here has been on non-metallic gears. So how can you make gears out of plastic perform just as well as their metal counterparts? So we're developing the design methodologies, we are developing the materials to enable us to really push the boundaries of those gears. I think with continuous work on materials, coupling that though really importantly with understanding the material properties, with understanding how you design gears, we can really start to push the boundaries of those and start to see eventually fully polymer gearboxes.
Storage energy, that research has been going on for a while, and that particular technology is started about 12, 13 years ago. It's about storing energy in the form of liquid air which is like a liquid, but you just freeze air down to minus 196 degrees C, and it becomes liquid like a water. So, and in that way, energy is stored in the liquid air. So when you need the energy out, electric out, what you do, you pump it up to a higher pressure and you use environmental heat to heat it up, which will expand by about 700-800 times, and to drive a turbine to produce electricity. So energy back to the grid. Then you can use the energy whenever you want. It's like a battery or like a bank. When you need money, you just take money out, use cash machines. That's the way it works.